Hello, my name is Kevin Benton and I will be doing a presentation on mathematical induction. Mathematical induction is a mathematical proof most commonly used to establish a given statement for all natural numbers. However, it can be used to prove statements about any well-ordered set. It is a form of direct proof and is done in two steps. The first step is known as the base case, and that is to prove the given statement for the first natural number. The second step, known as the inductive step, is to prove that the given statement for any one natural number implies the given statement for the next natural number. From these two steps, mathematical induction is the rule from which we infer that the given statement is established for all natural numbers. The method can be extended to prove statements about more general, well-founded structures, such as trees. This generalization, known as structural induction, is used in mathematical logic and computer science. Mathematical induction, in this extended sense, is closely related to recursion. Mathematical induction in some form is the foundation for all correctness proofs for computer programs. Now, in some examples that I will be showing later on, some of them will not be using the natural number symbol, which is just an n. Some of them will use the integer symbol, which is a z. Now, but they are still natural numbers because all integers are natural numbers. Well, some of them are, not all. In an inductive argument, demonstrating the first condition above holds is called the basis step, while demonstrating the second is called the inductive step. Further, the assumption that this statement holds for n equals k for some particular value of k is that necessary to demonstrate the inductive step is called the inductive hypothesis. There are several variations on this theme. For example, one can argue inductively that a statement holds for all integers n is greater than 0 by showing that 1, it holds when n is equal to 0, and second, when it holds for some n equals k, it must also hold for n equals k plus 1. Alternatively, one could argue that a statement holds for all positive even integers by showing 1, that it holds when n is equal to 2, and for when some n is equal to k, and it must also hold for n is equal to k plus 2. So now it is time to show you some of my examples. Now, one of my examples is I'm trying to prove by mathematical induction that a times r to the n minus 1 is equal to a times 1 minus r to the n all over 1 minus r. Now, so for step one, we show true that n is equal to 1, and so that way we replace n, all the n's in that equation, to 1. So we have a times r to the 1 minus 1 equals a times 1 minus r to the 1 all over 1 minus r, which basically the 1 minus r's on top and bottom will cancel out. And then on the left hand side, a times r will be a times r times 0, which anything to the 0 power is 1. So then that step is true because a is equal to 8. You can see from right here. Alright, step 2 is that we assume truth that n is equal to k. So we write out all of what the original problem stage. So that would be right here. And for that, we have, so then that way we replace all the n's with k's. So step 3 is now trying to prove true that for n is equal to k plus 1. So thanks to step 2, well, first off, we write out the whole problem again, but this time we substitute every n with n to the k plus 1, except for one number before that. So thanks to that, as you can see right here, I was able to substitute that in with what we got from step 2. So that way, I got a times 1 minus r to the k all over 1 minus r plus r to the a times r to the k times 1 minus r in parentheses all over 1 minus r, which is equal to our right hand side. So I distributed I distributed to the parentheses, and since I had the same denominator, I just combined the two terms. And so then I got a minus a to the r times k plus a to the r k minus a to the r to the k plus 1. So then I could eliminate the two to the negative a to the r k and the positive a r to the k. So then I'm left with a minus a r with the power of k plus 1 all over 1 minus r. And so with that, I took out an a, and then I was left with a times 1 minus a, not a, 1 minus r k plus 1 all over 1 minus r, which is equal to our right hand side, which was a 1 minus a k plus 1 all over 1 minus r. So hence, by mathematical induction, p of n is true for all n. And you can see this right here. This is where we substituted. Oops, I'm sorry. This is where we substituted in. And then, so after we substituted in, we got that right there. That is where I combined and I'm sorry. That is where I combined and I eliminated the two a times r to the k, and that is where I got in here. Then that was the end of my proof. Now another example is I am using, I'm sorry, I got allergies. I'm using trying to prove by mathematical induction these two matrices, as you can see right here. Okay, so for my first step, I must show true that n is equal to 1. So on my left hand side, I have my matrix 1, 2, 0, 1 raised to the first, and then on my right hand side I have 1, 2 times 1, 0, 1. So then anything to the first power is itself, and anything times 1 is itself. So then that's where I get both of them equal and true. So that way now I can move to step 2. And now step 2, just like our previous example, is that we must assume true for n is equal to k. So now we replace all the n's with k. So as you can see, right here. Can you see it? Yes. As you can see, I replaced my original problem. I replaced the n right there with a k, and I replaced this n with a k. So now I move on to step 3. And step 3 is to prove true that n is equal to k plus 1. So now everywhere where I have a k, I add a, everywhere where I had a k, I put a k plus 1. So now I have a, as you can see right here, I have my k. I have my k plus 1, because if you multiply these two out, it's k plus 1. And so, thanks to our step 2, we can substitute this function in, and then that's where we get the 1 2 to the k 2 times k 0 1 times 1 2 0 1. It is equal to our right hand side right here. So now we work out our second portion here, and what we do is we use a system of equations, and so we do right here, we do it times our numbers on this row, and so right here you also do it on times this row, and for this one we do it times this one, and for these we do it times this. So after that we end up with 1 2 times k plus 2 0 1, and that is equal to our right hand side. So hence by PMI, P, which is equal to mathematical induction, P of n is true for all n. Now, some famous mathematicians that use this are Euclid, Bhaskar, Pascal, and Fermat. There have been many others, but mainly I have these four. Now, Euclid used mathematical induction for was his proof that there is an infinite number of primes. Bhaskar used it to come up with the cyclic method. Pascal used it for Pascal's triangles, and Fermat for his Diophantine equations. Now, however, the first two, I meant to say, however, the first two didn't really explicitly state the second step, which is to use the inductive hypothesis. So the first true mathematical person to use mathematical induction would be Pascal and his triangles. And what Fermat would be next, which he used a related principle, which is the indirect proof by infinite descent. So not only can mathematical induction be used for proofs, it can also be used for proving functions in different areas of mathematics. You can use it to prove the Fibonacci numbers in algebra. In geometry, you can prove that a square may be cut into any number of smaller squares greater than 5 with no leftovers. Give me 1 second. In combinatorics, you can find different patterns. For an example, uh, is that on the first cell of a strip of squares sits a grasshopper. Each minute it jumps to the right, either to the next cell or on the second to next cell. You can find the number of ways that it can reach the nth cell. So, thank you for watching this on my presentation for mathematical induction.